Okay, so we're gonna talk about floating point numbers. And at first, these numbers can seem a bit intimidating because they've got all these weird terms. There's a bunch of implicit items here, and we really don't know how to look at a series of ones and zeros that's supposedly a floating point number. So to tackle this problem, we have to understand what we're talking about. What we're trying to represent is numbers of any size, not just fractional numbers, but numbers of any size in binary. And floating point is essentially just scientific notation. And we need to look at scientific notation in base 10 and understand how it works. If we have a number 16.75 in base 10, and we write it in the normal way with the decimal point after the ones column, here being this being the ones column, we can see that there's an implicit 10 to the 0 at the end, as in we're multiplying all of this by 10 to the 0, which is just 1, which shows you that 16.75 is the number that you're representing. But if we wanted to put this in scientific notation, we need to shift this decimal point so that it's after the most significant digit. The most significant digit here is the 1, and before that is all trailing zeros. So if we move the decimal point here, we can see that we've moved the decimal point, but this is no longer the ones column, this is now the tens column. So we need to account for that. We need to show the reader that we need to multiply this whole thing by 10 to get the original value. And you can see this times 10 to the power of 1 here represents that. And now there are two ways of thinking about this 10 to the power of 1. The first is seeing the 1 and noticing that you can just move your decimal point one place to the right to get back the original number. If it was negative, for example, you'd move it to the left to get a smaller number. The other thing you can think about is just simply moving this 10 to the 1 over your most significant column, and you end up with your new columns perfectly aligned. This 1 is now correctly the 10 to the 1 column, the 6 is the 10 to the 0 column. The decimal point magically appears here after the 10 to the 0 column. 10 to the minus 1, 10 to the minus 2. We've got our original number back, 16.75. So we've converted from and to scientific notation, to and from scientific notation. And really all we need to do is extend that to binary and add in a few special cases, basically. So in binary, we're in the habit of writing numbers in 2's complement form, which you can visualize as the first bit being a negative value. So here's our number, 16.75, written in fixed point notation with the binary point 3 bits from the right. And as you can see, there's our implicit 2 to the 0, just as we had here with the 10 to the 0. So the implicit 2 to the 0 basically means that this number doesn't need to have its binary point shifted anywhere to be read. What we can do is convert this into scientific notation by moving the decimal point so that it's after the most significant bit. Now, you would think that that would go here because that's the first one and before it is all zeros. But actually, since we're using 2's complement, we need to count this 0 as a significant bit. And I'll explain why later. Or you'll see why later. So if we move this decimal point here to the left, we've moved it 1, 2, 3, 4, 5 places to the left. That means in order to get back to our original number, we would need to move the decimal place 5 places to the right, which means our exponent is 2 to the 5. We can also see that by looking at the column of our most significant digit, which is actually 2 to the 5, ignoring the negative. So, what we've established is that we can convert this fixed point number into floating point simply by moving the decimal point and then reminding the reader what the exponent is. Once you convert that back by either moving the decimal point 5 places to the right because of that positive 5, or by just placing the 2 to the 5 over the most significant bit. You can see that we have positive 16.75 we've converted back and forth. Now, these floating point numbers aren't stored with the times 2 to the power of, and they aren't stored with the decimal point, because the computer knows that the decimal point is always going to be in the same place, and the computer knows that there's going to be a times 2 to the power of before the exponent. So all the computer needs to store is some number of bits for the mantissa and some number of bits for the exponent. And these are specified by the format of the floating point number. So this format here would be 8 bits for the significand or the mantissa and 4 bits for the exponent. The base and the point are implicit because they're always going to be the same. Now bear in mind that this is not the standard for floating point notation, but it's the one that we're going to use. This form of floating point notation uses 2's complement to represent negative numbers. So we'll see that on the next slide with a negative number here. So let's see we're given this number, and we're told that the floating point format is 8 bits for significant and 4 bits for exponent. We add in the implicit things that we know are there. There's a decimal point after the most significant bit, which is always going to be the first bit if it's in scientific notation, because we've normalized it. Normalized meaning we've moved the decimal point to where it's after the most significant bit, which we did in base 10 as well. And then we add in the times 2 to the power of. I've also in green here converted this number to the base. Oh, where's my mouse gone? I've converted the exponent into decimal. Once we do that, we have kind of done 2 steps in one here. First thing we've done is move the decimal point to its correct location by moving because it's a positive 3, we move 3 to the right. 1, 2, 3. Decimal point is there. And the other thing we've done is labeled the columns, which you could have actually done in one step simply by putting 2 to the 3 above the most significant bit. And since we're in 2's complement notation, that most significant bit gets its negative value. And that's how we know it's a negative number, because the first bit is 1. Just like in any 2's complement number, it's the same in floating points, in this format of floating points. So now that we have it into fixed point, we can easily convert it into a decimal number. There's 2 ways of doing that. One way is to take this as -8 and then add the rest, which would work. Or we can 2's complement the number and remember that it's negative. Once we 2's complement it, we get a negative of this number. If we evaluate this in binary, we get 2 plus 1 over 2 plus 1 over 16, which gets you 2.5625. Remembering the negative, we get negative 2.5625 in base 10. So that's how easy it is to convert from floating points into decimal numbers. Just remember that if your exponent is negative, meaning you're representing a really small number, you'll need to move your binary point to the left. So positive is to the right, negative is to the left of your decimal point. But the easiest way to think about it is to just place 2 to the power of this exponent on the column of your most significant bit. And the convention is that we leave the most significant bit as being the 2's complement bit, which means that it is possible for the first digit to be 0, which it's not in decimal. If it's in decimal, the first digit of a scientifically notated number has to be between 1 and 10. So, as you can see, it's not that hard to convert to and from floating point in binary, because it's simply scientific notation. All you're doing is moving the binary point left and right. So once you understand how to think about it, it becomes quite easy to convert it. There you go.